Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to session 2 of the series of presentations on engineering geology. In this session we are going to talk about geologic structures, different types of landforms. We will try to recognize what are the various landforms that one might have to encounter while working as an engineering geologist. But before we get into the subject matter of today's presentation, I am going to take up the question set that I gave in the first of this series of lectures, and I am going to try to provide you the answers of the question set. The first question that we had in the last presentation was how engineering geology differs from geotechnical and geological engineering. Now, the difference is essentially very tenuous. Only thing that I can think about is engineering geology is more inclined towards the geologic matters, while geotechnical and geological engineering deals primarily with the mechanical aspects of the different problems that are encountered in engineering geology. Then the second question that I asked was that what are the key factors that may trigger slope failure. Two of the major factors that causes slope failure are loss of strength, loss of shear strength of the material of which the slope is comprised. The major reasons for the loss of shear strength is basically rise of groundwater table, or it could be because of weathering effects and consequent deterioration of shear strength of the material. Now, the other thing that often causes slope failure is human activity. For instance, as we talked about in the last presentation, if we oversteepen a certain natural slope, sometimes that also may increase the likelihood of slope failure. The third question that I asked was what are the indicators of impending slope failure. Now, this I discussed in the passing when I was making the presentation the last time, and one of the major indicators of impending slope failure is appearance of cracks near the top of the slope. If such cracks are detected while inspecting a slope, that is taken by engineering geologists as indicator of impending failure of the slope. The fourth problem that I asked was what are the factors that initiate ingress of salinity. Now, the factors that initiate salinity ingress include the lowering of groundwater table or rise of seawater level, or both. Major contributor is really lowering of groundwater table and the differential in head of the saline aquifer and the freshwater aquifer, that actually is the driving force that causes salinity to enter the otherwise non-saline groundwater condition. So, that actually in a nutshell the solutions to the questions that I asked in the last time around. you can elaborate on these ideas, and now we begin with the subject matter of today's presentation. We begin with trying to summarize what are the objectives of this particular presentation. We want to learn what are the different types of landforms, as I indicated earlier. How do you geometrically describe the different types of landforms? What are the different stratigraphic units, how they are related to each other, or what are the characteristics of the contacts between different stratigraphic units. And we want to also recognize a number of common geologic landforms that you might actually have to encounter if you decide to work as an engineering geologist. You need to understand what are the problems or what are the advantages that you might have to deal with when you try to handle a project in those kind of landforms. So, these are the objectives of this particular presentation. The objectives are listed on the slide that is up there now, which I just discussed. Now, we actually begin with the subject matter. What are the composition of geologic structures? Now, you can imagine that geologic structures are comprised of different types of soils and rocks. These things we call as geologic units. So, geologic units means different types of soils and rocks. Now, these different geologic units are going to be in contact with each other. Now, these contacts also are an essential part of a geologic structure. So, we need to describe how the different geologic units are in contact with each other, as well as what are the geometry of each of these different geologic units. Let us look at an example what I mean by different types of geologic structures. Now, the slide that is there now, to the right of it is a photograph of an excavation through a site underlain by different layers of soils. Now, you can see that near the top of this particular sequence of soils, you have got an organic a layer of soil which has got some organic content. So, this is the layer in which you have got some organics. The roots of the overlying vegetation actually penetrates this layer, and there are activity of different types of organisms. Then underneath that layer is a sequence of primarily granular soils of brown color, which extends up to the bottom where the shovel is kept. So, this is the layer of basically sands, silts and gravels. Underneath that sand, silt and gravel sequence is a layer of clay of gray color. So, this is the clay unit, and this one here is the unit that comprises granular soils. So, here you have got several different geologic units. Then basically you have got an organic layer near the top, and you have got a granular a sequence of granular soils underlain by a layer of clay. And you have to notice that the contact between each one of these layers are sometimes near horizontal, and sometimes they are dipping either to the left or to the right of this particular picture. The drawing to the left of the slide here actually shows a vertical slice through an older rock, which is shown by a set of multicolored folded lines, and on top of it there is another layer of younger rock which is comprised of not folded, I mean relatively straight, relatively flat layers of younger rock, relatively flat layers. Now this kind of in this sequence what you have got, the upper unit, you have got two geologic units there, the upper one comprised of younger rock and the lower one comprised of older rock, and in between there is a contact which is called unconformal contact, and we are going to discuss the details of this kind of different types of contacts when we discuss the characteristics of contacts in the next little bit. First we try to look at the geometric properties, how to describe different geologic units in terms of their geometry. Now what you need to describe? You need to describe the thickness of the layer, and that thickness actually could increase or decrease as you proceed in a certain direction. Then you have to talk about the inclination of a particular layer, and that inclination is given the term dip, and also you have to talk about the orientation of the intersection of that particular geologic unit, if actually there is one, at the ground surface, and that intersection of the geologic unit with the ground surface is given the name strike. This whole description is actually illustrated with the sketch to the right of the slide there. So dip of the layer is shown here, then the strike of the layer is shown here. Now this one here is the ground surface in this case, and the dip and the strike shown on that sketch there actually describes this geologic unit. Now there is another thing that one needs to know, what is a true dip and what is an apparent dip. Now you can imagine that the slope of the layer that is shown on the picture there will depend on the direction in which the slope is given. Now if for instance in this case we describe we give the direction of the slope in this direction, or we give the dip, we provide the dip in this direction, that is going to be different from the dip that is going to be obtained when one measures the dip in that direction. Now the maximum slope of the different among the different directions in which the dip can be provided is called the true dip, and all other dips, I mean the dips in any other direction are called the apparent dips of that particular layer. Okay. Now we can describe different types of geometry of geologic units. We now want to get into different types of geologic structures that you are likely to encounter if you work as an engineering geologist. The first type of geologic structure that we consider here is called folds. Now, the sketch that is shown there actually schematically presents a series of folds. What is in this case we are actually looking at a vertical slice through a bedrock, and you can imagine that generally what happens, as we go deeper, the age of the bedrock actually is increasing. Now, what are the causes of development of this kind of folding? Folding develops because of changes in stress regime, or it could develop because of intrusion into the bedrock of another type of rock. For instance, there could be an intrusion by volcanic rock through an overlying bedrock, that could also cause a fold to develop, or we can or folding can develop because of tectonic activities and uplift. Now, we illustrate each one of these things in the next little bit. Let us consider how folds develop when the regime, the stress regime actually changes. Let us consider a sequence of bedrock sequence comprised of bedrock, different bedrock layers that are shown in the sketch. Let us consider this sequence of bedrock, and this one here actually shows the shallowest layer, and as we go down deeper we get into green and cyan colored layers. Now, say we want to apply a compression in that direction, then what we are going to end up with is a bedrock that is going to look like this eventually. So, that is how actually folds develop. That is how folds develop when a sequence of bedrock is subjected to an increase in the regime of stress in a given direction. Now, as the stress regime increases, then this particular fold is going to become steeper and steeper, and eventually it is going to be it is going to actually fold over onto itself, and finally if the stress regime is increased even further, then these different layers of rocks will be torn apart, and that kind of a situation is called faulting. So, that is what I explained in the sketch in the previous page actually is illustrated in the series of folds here. So, as we go to the right of this particular sketch, then the compression is actually increasing in that direction. So, when we are on the left, to the left, the folds are gentler, and that is to the left folds are gentler, as you can see here. In this area the folds are gentler, and as we go to the right, then the folds are becoming steeper and steeper. Actually they are the limbs of the folds are coming closer together, and eventually to the extreme right the layers are torn apart from them from each other, and that is called the thrust faulting. Now, there are different definitions in this connection we have to consider. One is the definition of anticline. Anticline is actually a hump like body. The central part of it is a little bit at a higher elevation than the right and the left flank. So, this kind of a situation is called an anticline, and the reverse of an anticline is a syncline, which is shown just to the right of the anticline here. Now, a symmetric fold is a fold which is actually has got for which the two arms are actually symmetric. So, both the folds to the two folds to the left of the sketch here actually are symmetric folds, and asymmetric fold is one on the other hand for which the two limbs, the characteristics, geometric characteristics of the two limbs are not identical. For instance, the fold shown here is an asymmetric fold. You can see that the dip of the left limb of the fold is much gentler compared to the right limb of the fold, and when the compression increases further, then the folds, the different units actually they come even closer together, and we get an overfold which is to the further to the right, and finally the fold completely closes in that, and that situation is given the name recumbent fold. So, this is actually an example of how folds develop because of the change of stress regime. Now, let us consider how folds could develop because of tectonism. Now, say you have got a bedrock that is underlain by two blocks of another unit of bedrock, and these two blocks are they try to move relative to each other. So, let us consider that this block goes up and this block goes down. So, what could happen actually that you get a configuration which looks like this once the movement is over. So, if there is that kind of configuration, then the overlying layer is going to take a final configuration that might look like that. So, in this area, because of the movement of the underlying bedrock, a fold is developing. So, this is folding because of movement of an underlying fault, of a fault. We are going to actually learn more about fault in the next little bit. What do we mean by fault? As illustrated in the last sketch, when actually rock masses are crisscrossed by a joint, I mean there are different blocks of rocks that are actually underneath a particular site. Now, these blocks sometimes try to move relative to each other. That could be because of several different things, again because of stress regime change, or because of intrusion, or because of seismic activity in the nearby location. Now, basically the movement is initiated by accumulation of strain at the interface between two blocks of rock, and if that leads to a failure, that actually causes different blocks to move relative to each other. and that is the from the mechanical point of view, that is the cause of movement of fault. Now, the two blocks can move relative to each other in several different ways. Now, depending on which way the faults which way the blocks move with respect to each other, that causes different types of faults to develop. Now, we have to consider different types of faults then, and the types of faults that are encountered usually are normal fault, reverse fault, strike slip fault and oblique strike slip fault. Now, what is meant by each one of these faults is going to be explained in the next few slides, and you have to understand that basically the classification of the fault means that the relative movement between the two blocks that are on either side of the fault are of different types. Now, let us first consider what we mean by normal faulting. The sketch that is shown on the slide there, it actually shows two blocks separated by a plane. The plane that separates the two blocks is shown here, shown there, that is the plane that I am talking about. This plane is called the fault plane. Fault plane. Now, fault plane essentially separates two blocks on either sides then, and the two blocks are going to try to move with respect to each other. Now, let us see what kind of movement we are going to get in normal faulting. Watch the animation here. So, that is how normal faulting is going to develop. This is the ground surface. You might have understood that already, that is the ground surface, and different layers of rocks and soils are shown using different colors. So, this one essentially is unit 1, that is the surface layer. Then you have got unit 2, that could be another soil layer, and this one here is unit 3, which could be a rock layer. Now, we have to describe the geometry of normal faulting. This particular slope, this portion of the slope is called the fault scarp. So, that steep portion of the slope is called the fault scarp. Now, the direction in which the fault intersects the ground surface is called the strike of the fault. So, that is the strike of this fault, and the dip of the fault plane from horizontal is called the dip of the fault. In this case, this is the dip of the fault. Now, again, as we discussed earlier, the dip of the fault could be an apparent dip or a true dip. So, the azimuth of the strike has to be provided for a given fault. One has to also provide the dip of the fault along an azimuth, and also maybe true dip of the fault and the azimuth in which the true dip occurs. So, this is how a fault is described. We also have to define another term here, and that is called the throw of the fault. A throw of the fault is actually measured along the fault plane, that actually gives the maximum movement of the fault which is shown there. So, this one here is the throw of the fault plane, throw of this particular fault. So, we need to then describe the throw of the fault, we have to describe the strike of the fault, and we have to describe the dip of the fault. Okay. So, that is normal faulting. Let us watch it again. This is how normal faulting develops. You can understand that normal faulting develops when a tensile regime, actually when we try to pull the two blocks on either side of the fault plane apart from each other, then we develop a normal fault. Now, let us go to the next type of fault, and that is called reverse fault. Reverse fault is exactly opposite to normal fault, and the different features of reverse faulting is explained on the slide there, and you can see that reverse faulting arises because of a compressive regime shown using the bold arrows on either side of the two blocks, and in this case because of the compression, one of the blocks, the block to the right in this case, actually tries to climb on top of the block to the left. So, the block on the right is called the hanging wall, and the block on the left is called the foot wall of a reverse fault. Now, the throw of the fault and the strike of the fault are also indicated on the figure, and so is the dip of this particular fault. If a reverse fault becomes a very shallow angle fault, in that case the fault is called a thrust fault. So, thrust fault is a type of reverse fault in which the dip is very small. Now, we go and try to understand how the other type of faulting develops. This animation actually is going to show you how strike slip faulting develops. In this case, what we are trying to do, we are trying to apply a shearing along across the fault plane. So, we are trying to in this case we are going to we will try to push the block that is on the right of the fault plane further away while keeping the portion that is on the left of the fault plane at the same location. So, what is going to happen if we try to move these two blocks related to each other as we described? The animation actually shows the result of such a movement, such a deformation process. So, in this case again dip of the fault is going to be given by this angle. So, that is the dip. The throw of this particular fault is going to be this much. So, that is the throw, and this particular movement, as is evident, occurred because we want to apply a stress state as shown by these two arrows. So, we wanted to push the block that is on the right farther away, while we wanted to keep the block that is on the left side of the fault plane at the original position. This kind of faulting is also called a left lateral faulting. So, if you are facing the fault plane, the block that is ahead of you is trying to move to the left, to your left, then it is called left lateral fault movement, left lateral strike slip fault, while if a reverse fault movement takes place, then that kind of fault is given the name right lateral strike slip fault. Then we could also have oblique faulting, which is a mixture really between the normal faulting or reverse faulting and strike slip faulting. So, in this case again you have to describe the dip of the fault, that is shown here, that is the dip, and you also have to show the throw of the fault. So, throw of the fault is that much. So, that is the throw, and as usual strike of the fault is in that direction, and the fault scarp is that steep portion of the slope. Okay. So, we now get into other type of geologic structures, other type of important geologic structures. One of those structures we consider is an escarpment. Escarpment is essentially a steep bluff that separates two relatively flat areas of land. Now, an escarpment can develop because of erosional activity of water or air, or because of faulting or subsidence. We actually illustrate an escarpment, an evolution of an escarpment using a set of sketches on the slide that is being shown now. Here we have got an erosion resistant rock near the surface, and on top of it flows a river, and that river that erosion resistant rock is underlain by relatively softer erodible rocks. So, what happens actually, the splash, the water that splashes while falling like that actually causes the layer underlying the erosion resistant rock to erode and recede, and because of the recession of the erosion resistant rock, the block overlying because of the recession of the erodible rock, the erosion resistant rock actually there is an overhang actually is generated in the erosion resistant rock, and that overhang eventually gives way. So, that is shown on the rightmost sketch, and gradually the bluff actually works its way to your right. So, this is an evolution actually, or this is an illustration of how an escarpment evolves because of erosional activity of water flowing at the surface. Two other types of landforms, cuesta, mesa and butte. Those are illustrated with the sketches on this slide. Cuesta is essentially a long hill, one side of which is much steeper than the other side. So, it is very similar to an escarpment, but in escarpment the bluff is more or less vertical, and the two two sides of the bluff are quite flat. In case of cuesta, there are gentle slope on one side, and the other side as shown here is usually flat. This is also cuestas also develop because of difference in erosion resistance, and if particularly near the top you have got erosion resistant rock that juts out after the erosional activity, due to the erosional activity, and a cuesta develops as shown in the sketch on the top. The bottom sketch illustrates mesa and butte. These are essentially flat topped hills, generally develops in the in dry areas because of erosional activity once again. The essential difference between a mesa and a butte is that mesa covers a much larger aerial extent than the butte. If the area underneath the flat top of the hill is approximately 10 hectare or more, that is called a mesa. Otherwise, if it is smaller, then the hill is called a butte. We now try to understand, get an idea about different types of landforms that one might have to encounter in a fluvial environment, in an environment where there is water flowing through the ground surface like a river. So, river related landforms include alluvial fan. It also includes floodplain, oxbow lake, abundant channel, river terrace and delta. We will actually explain each of these individual terms in the next little bit. Now, this one here occurs in a hilly terrain while all the other ones are typical of flat terrains. Mind you, all these different type of landforms are because of flowing water. Now, let us see what we mean by each one of those things, each one of the terms that I listed there. Imagine a river flowing out of a mountain range. And it is hitting a relatively flat area once it exits the mountains. So, in that case what happens, there will be a lot of sediment load that it carries when the slope that it is passing through is relatively steep, and then once it hits a shallow slope, then the river actually tends to deposit the sediment load in the form of a fan, and this type of a structure is called alluvial fan. Alluvial fan is characterized by heterogeneous mixtures of sand, silt and gravel, and because of the heterogeneous nature of alluvial fan, it has got some advantages, like it actually is more resistant to failure during, for instance, an earthquake. So, these are the typical properties of alluvial fan. Now, let us see what we mean by a floodplain. If there is a river flowing through a relatively flat terrain, then what you might have seen already, that the river generally tends to meander. So, this kind of geometry of a river, when it is flowing through a flat terrain, we are looking at a top down view here, bird's eye view. This kind of a geometry of a river is called meandering river. When we take a section of a meandering river, then what we see normally is that the river bed is shown here, and on both sides of the river bed is a relatively flat land. This flat land is sometimes flooded when the river water level, this is the water level, normal water level, when the normal water level is surpassed and the water tries to overflow the banks, then the area that actually is flooded is called the floodplain. So, the floodplain actually could extend several kilometers on either side of a river until one gets an even higher, one enters an even higher ground. For some rivers the floodplain is very extensive, and for some other rivers, smaller streams, the floodplain is relatively of narrower extent. So, this is a section that we have drawn here, and that is the plan of this particular area. So, and here we show the ground surface like that. So, this area essentially is the floodplain. Okay. So, that illustrates what we mean by a floodplain. Now, let us see what we mean by a delta. When a river enters the sea, then it actually bifurcates in several different smaller streams before entering the river. This particular this type of triangular area through which those smaller streams actually crisscross before entering the sea, that is called the delta. So, this is a delta. The size of the delta also depends on the size of the river, and it could be actually several hundred kilometers across, as is the case in case of the Ganges river. On the other hand, for smaller streams there could be only a very small delta. Now, delta is typically crisscrossed by different channels, and these channels sometimes take a different course, and so a delta is actually crisscrossed by abandoned channels, and there could be saturated areas, saturated patches inside the delta, which used to be a water course earlier, and it is no longer active. Delta is typically underlain by sands and silts and gravel, whereas floodplain that we saw earlier is typically underlain by extensive deposits of silts. Okay. The other features is illustrated in this satellite image that is shown on the left of the figure. It is taken from a NASA satellite. Actually, this actually shows the river Ganges a little bit north of Kolkata. The river that is shown there is the river Ganges, as I mentioned, and here this is the water course. this one is the water course, this one is the water course, and you can also see in this drawing that there used to be an abandoned channel in this area, and then there are other features like an oxbow lake. So, this is an oxbow lake which used to be a water course earlier, but the water course is no longer active. So, this entire area is characteristics of floodplain and is typically underlain by silt or finer grain deposit unless one is in the actual water course that is active right now or it is presently inactive. So, the sketch on the right shows what I mean by that. So, the blue line is basically the existing water course, and the gray shading is shown to indicate the floodplain underlain by silts. The yellow line indicates river channels that are no longer active, and these yellow channels are actually underlain by sands, sandy soils, and the area that is on either side of the gray shaded area actually indicates the terrace or uplands, that is the extent, lateral extent, that actually is the lateral extent of the floodplain. Okay. Now, we have to consider there are geologic landforms that are due to activity of wind, and we normally get dunes and loess. Loess is essentially fine grain, I mean silt size particles blown by wind, and these are characterized by steep slope, and they are very susceptible to failure if they are I mean if water is they become saturated, they become prone to failure, whereas dunes are generally underlain by sand grain deposits. We could also have glacial deposits. Glacial deposits are listed here, and they are generally laid by ice. So, if they are directly laid underneath ice, they are called till. They could be glaciofluvial deposit, meltwater that originates from melting of glaciers like drumlin, esker or glacial outwash. Now, these things typically are elongated in the direction of the ice flow with their slope in the direction of ice flow in the up ice direction is generally gentler compared to generally steeper in comparison with the down ice direction. There could be glacial outwash deposit that are comprised of basically sand and gravel deposits, or there could be glaciolacustrine deposits that are fine grained deposits underneath glacial lakes. Okay, that in a nutshell summarizes different types of landforms. We looked at descriptions of different stratigraphic units. We looked at how to define them geometrically, and we tried to list a number of landforms that are encountered often in the branch of engineering geology. We finally end this session with a set of questions that you should try in your leisure, and again, as we did in the last presentation, I am going to provide brief answers when we meet for the next lesson. You should try to explain the dip, strike, anticline, thrust fault and loess. You should explain the slope on the windward on the and the lee side, whether the slope of a dune is likely to be steep on the windward or on the downwind direction, that is the lee side. And you should also try to answer whether a drumlin, what is going to be an orientation of a drumlin vis-a-vis ice movement. Okay. So, you try to answer those questions, and I am going to provide the solutions when I meet you again for the third of this series of presentations. Thank you very much. Hello everyone, and welcome to session 3 of the video course on engineering geology. In this session we are going to talk about geologic maps and stratigraphic sections. But as is the practice, before going into the subject matter of this presentation, I am going to first discuss the answers of the questions that were asked in the previous presentation. The first question that we were trying to answer was the explanation of the following terms: dip, strike, anticline, thrust fault and loess. Now, the meaning of these terms was clear from the presentation of the last lecture. To restate what I did in the last time, for example, let's take an example of a fault, and the fault looks like this. So in this case, dip of the fault is that angle there, strike of the fault is the orientation of this line perpendicular to the plane of this paper. I mean, the azimuth of that line is going to be giving the strike. Azimuth of this line is equivalent to the strike of the fault. So that is what we mean by the terms dip and strike. Then by syncline and anticline, what we mean is, if you have got a fold like this, then that one is called an anticline, and the reverse is a syncline. All right. Getting back again, thrust fault, what we mean by thrust fault is, say you have got a fault which is essentially a shallow angle fault, and we subject these two blocks actually, to a compressive load like that. Then this block is going to try to ride on top of the other block and eventually take a shape like this, and this block is going to get eroded out, and this kind of faulting is called a thrust faulting. Okay.